Good morning, everyone. Today we're going to see a very brief introduction to deterministic chaos, because it has some similarities, but also very important differences with complexity. However, it's also important for problems or situations that require adaptation. So it's useful to understand a bit more about deterministic chaos, even when we will not go so deep in the class in it from the theoretical side, but it's very useful to have a better understanding because we will encounter every now and then chaotic dynamics, as we mentioned in the previous class. So let me share my slides. Okay, I trust you can see them. So we'll see a brief review of the previous class, and we'll define in rough terms what chaos is, and we'll use the logistic map to better understand what's the mathematics behind chaos. Also, bifurcation diagrams and universality. So last class we reviewed some things about computation. If you miss it, it's available on YouTube. And we saw there are different definitions of computation. A most general definition is simply the transformation of information. So that can apply to almost everything. To every process. We can describe almost any process as a computational process because you have an initial state and a final state or a subsequent state. You can say that something computed that transition. However, theoretically, Turing defined computable functions as those that can be computed by a Turing machine. And so that's computation in theory. And computation in practice would be simply whatever we are able to calculate with our accessible means, be it with our fingers, with our phones, with a quantum computer, or however. So there are all these different types and perspectives of computing. We also saw briefly the implications of the information revolution, which, let's say, has allowed us to increase our computing power, our transmission capabilities, our storage abilities, and these have been increasing more or less exponentially, but they're starting to level off. I mean, the growth, at least in number of transistors in processors is not increasing exponentially already for more than 10 years. And we saw how complexity that we already saw that it's characterized by interactions that generate novel information. This novel information may create non-stationary problems. This means that when we are computing something, then the underlying conditions of the computation will change. So it will be similar as during a Turing machine is processing, let's say, some initial state. Then if we make some change on the tape or some change in the program or some change in the states, the allowed number of states, which is called the alphabet, if we make changes on that, then how can we continue computing, and how can we find the right output or a desirable output in spite of that non-stationarity, and in some cases even be taking advantage of that non-stationarity. So this we'll see in the next few classes, but it's important to have this basis to understand what are the implications of complexity, why we're able to study it only now with computers, and the difference between stationary and non-stationary problems, because if they're stationary, then traditional techniques are useful, even if we can describe a system as complex. If it's if at the time scale that we are studying it, it can be usefully described as stationary, then let's say we don't need to invent new techniques. The traditional techniques will suffice. Or better said, if the problem changes slower than we can compute solutions for it, then we can just constantly compute traditional solutions. But if our predictability is so limited that our solutions will be obsolete by the time we reach them, then we need adaptation. Let me see. I think I didn't compile the latest version of this. Let me quickly try to double check. Yeah. Excuse me, let me just open this. And yeah. So we could assume naively that if a system is determinist, then we can predict it. And this idea is different from the limited predictability of interactions that we already saw with cellular automata and with other examples. So let's say going back to Laplace's demon. So Laplace proposed if we have higher intelligence, so-called a demon, that has access to all positions and momentums of all particles in the universe, assuming they are elementary particles. Since these follow Newton's laws, as it was thought back then, and Newton's laws are reversible, you could predict all the future or all the past of the universe. So that was what Laplace proposed. I'm not sure whether Laplace believed that that could be made, but it was like a thought experiment to try to guide development in physics. Pankaj asked whether the slides are available in English. Some of the lectures are available in English. Some of them are only in Spanish. When I was giving this course in Spanish, it was the opposite. Some of them are in English, some of them are in Spanish. But yeah, I trust you can follow them. Just listen to me in English. So the main idea of Laplace's demon is that it's kind of framed the perspective in physics and science in general, even to our day. I mean, many people still try to pursue that dream of being able to predict everything, and the fact that we can't is just because of our limitations. However, it was seen that with the development of thermodynamics, that so Shoichi asks whether Maxwell's demon, that's a different demon. So there's Laplace's demon, and Maxwell's demon is actually related to what I'm about to say about thermodynamics. That when thermodynamics were better understood at the end of the 19th century, beginning of the 20th century, they realized that many systems are non-reversible. These are called dissipative systems, and it's very simple. It's simply that you have many states, and different states can lead to the same state. So if you are in a state and you have various predecessor states, you don't know where you came from. So basically you lose information, and that makes systems non-reversible. So this is related to Maxwell's demon indeed, because the idea of Maxwell's demon is that you have like a chamber with division, and you have a demon that can selectively allow some faster particles into one side and then slower particles on another side, and then in theory you could extract work out of that, or another way of well, it's a way of explaining the second law of thermodynamics, that basically in a closed system entropy tends to increase, and it's basically, you could start with the opposite. Now you have a box with a division, and one part is colder than the other. Basically, the colder particles are moving faster and slower in the other one. So in theory, when you remove the barrier between these two sections of the box, they start to mix very quickly, and then the temperature will be homogeneous. Basically, that you cannot distinguish different parts of the box. If you look at one part, it will have similar properties, statistical properties, to another part of the box. And so yeah, this is because it's more probable to have like a homogeneous state than a heterogeneous state in thermodynamics. In other systems, these things change. So yeah, that was to limit Laplace's demon towards the past, towards the future. The development of quantum mechanics kind of limited this idea, because as well there's the uncertainty principle proposed by Heisenberg. So that limits how much you can know about quantum particle. And this, let's say, was dismissed by some because they say, well, we don't even understand quantum mechanics, and we don't see these effects at the classical level. So at the classical level, we should still be able to predict the future. And what we understood around the middle of the 20th century, even when it has its roots in the late 19th century, is that non-linearity limits predictability. And I have the story of Poincaré. Yeah, I should tell the story of Poincaré. So the Henri Poincaré was a very famous French mathematician. He was also contemporary of Einstein. And in the late 19th century, there was a prize, I think, launched by the King of Norway, if I'm not mistaken. And the challenge was to solve the three-body problem. So Newton had solved the two-body problem with the law of universal law of gravitation. And the challenge was like, well, how difficult could it be to add a third body? So assume you have two stars and one planet. What will be the trajectories of these three bodies? And Poincaré didn't solve the problem, but he won the prize because he showed that he didn't have a trivial solution. And in the 1950s, this was better understood already with the help of the first computers. And this was named chaos. And we'll see why. I mean, it's not that it doesn't have a solution, it means that the three-body problem is chaotic. And this has limitations to how traditionally calculations were made. And actually the solar system is also chaotic because it's how many bodies in the solar system? It's well, if you consider comets and asteroids, it's a lot. If you consider planets, how many we have now? 8? I don't know, it keeps on changing. So plus the sun, so it would be like 9-body problem. And of course the sun dominates the dynamics. So if we look at short time scales, we can predict with very high precision, just like we can predict with high precision at a short time scales in chaotic systems. But in the scales of billions of years, let's say the small effects. So for example, there is a very small effect of Jupiter on the orbit of Mars. And that limits the predictability of where will be Mars in a billion years. So we can predict, let's say, in the scales of thousands of years, but not millions of years. And what limits this predictability is nonlinearity. And before going further, I should explain what nonlinearity for those who don't have a mathematical background. So a linear function is basically one that can be represented with a line, but to understand what it means is simply that if you have, let's call it an input, and there's some change in that input, that change will create a proportional change in the output. So that would be a linear function. It's proportional. And it could be, let's say that the input is twice the output, or the output is twice the input or half the input. But if it's proportional, then it's linear. And when it's not, then it's nonlinear. It's a bit redundant, but let's say the implication is that with nonlinear functions, which could be a sine function or a parabola function or a polynomial function, exponential function, what you have is that for some regions of that function, it could be that you have very large changes in the input, and this will produce no change in the output. So you're like putting lots of effort and then nothing happens. And then on the other extreme, you could have very small changes, and then that creates very small changes in the input, and this will lead to very large changes in the output. And this is what characterizes chaotic dynamics. We'll see in a moment. But an example of a nonlinear function is just imagine the the weight on a camel's back. So in the x-axis, you start increasing the weight, you increase, and here you can plot, I don't know, the height of the camel or something, and you can add weight, and the camel will withstand the weight, and it doesn't change. But then suddenly there's the small branch that breaks the camel's back, or doesn't have to break the camel's back, just the camel falls because it's too much weight, and then you have a sudden change. So that's not a linear function. So if you are in one region of the input space, nothing changes, and then you give a little step, and then there's a drastic change. That's an example of a nonlinear function. So chaos mathematically is defined with something called Lyapunov exponents, but I will explain this in a moment. So imagine you have two initial states that are very similar. So in the first line, there are two numbers that have a difference of 1 digit in the 10th decimal or something like that. But then as we follow the trajectories in time, they will lead to very different future states. So this is called sensitivity to initial conditions. Small changes in the initial condition lead to huge differences in the future. And it doesn't matter that we have 20 digits of precision or 200 digits of precision or 1,000,000 digits of precision. Eventually, these states will diverge because there's what is called an exponential divergence of trajectories. So and this is what characterizes chaotic dynamics. So mathematically, chaotic system, it's one in which at least one variable has a positive Lyapunov exponent. And what's a positive Lyapunov exponent? So Lyapunov exponent is something that measures how fast similar trajectories diverge. So what's a trajectory? you have different variables, and then this change in time, and then you follow, you kind of draw the value of these variables in time, and that's the trajectory of the variable. So if you begin with very similar values and these diverge exponentially, meaning that as time passes, the differences between these two values, which initially were small, increase more than more and more and more and more, meaning exponentially, then the Lyapunov exponent will be positive. If they converge, then the Lyapunov exponent will be negative, and then you have order dynamics. And when the Lyapunov exponent is close to zero, it means that the trajectory is neither converge nor diverge. And some people call this complex dynamics or critical dynamics. We'll see about that in a few classes. About these three different regimes, which can be characterized with Lyapunov exponents: negative order dynamics, zero or close to zero critical dynamics, positive chaotic dynamics. So when a dynamical system has positive Lyapunov exponents, means that it has chaotic dynamics. We find that their attractors are self-affine, meaning that they're fractals. So the attractor is the subset of the states of a system that attract the dynamics. I mean, of course, it's in the name already. So, for example, a pendulum has two attractors, one stable, one unstable. So, yeah, I'm trying to show a pendulum. So, let's say the pendulum at the bottom will be a stable attractor, and if you perturb it, it goes back to that state, to that attractor, and yeah, that's why it's called stable. So it, you move it and then it goes back. But then if it's the pendulum on top, you can imagine trying to balance a broom on your hand. So if the initial condition is like very precise, it will stay there. But a very small perturbation, it will lead to the system going out of that state. So that's why it's unstable. A very small perturbation will kick the system out of that state. And in many systems, you have like either point attractors, meaning that there's just one state and the system stays there, like a pendulum in the resting state. In others, you have cycles, like circadian rhythms, so or human cycles also could be like that. Like we go from bored to tired to bored to tired and so on, and it's just a cycle. But chaotic systems have fractal attractors, and we will see what does that mean. So these are just example of some chaotic dynamical systems, and well, the attractors, and you can clearly see, well, not clearly see, well, there's some self-similarity in there. So yeah, they're fractal. We will see now more examples and explain what do we mean by this fractality. What do we mean by self-similarity? So the important thing is that the attractors are a subset of the state space in most cases. It's not that the system just goes wherever it wants, but it does mean that within that attractor, it's very difficult to predict where the future, where the system will be in the future. So these are more examples of strange attractors. And in order to understand this better, we will use the logistic map, which is this function f of x equals ax times 1 minus x. So it's a parabola. And this is restricted to the interval of x between 0 and 1. And it describes population dynamics. So the constant a would represent the growth rate or the fertility rate. And this value is restricted between 0 and 4. And then we call this a map because the function is iterated several times. So we have an initial condition, x0, and we apply this function to x0, and we will get x1. And then we apply the function to x1 to get x2, and like that to get xn, which is iterating the initial value n times over the same function. So the set of all iterations is called the map of f. So basically, we just repeat the same operation. And let's say we can also do this graphically. So this is a plot of the logistic curve. This is the identity line, which is useful to manually make the mapping. So, for example, if we have this initial state 0.1 with a value of a equals to 2, then f of x0 will be this value in the parabola, which is a bit less than 0.2. And then if we move to the identity line, this will be x1 again, and then we move to the parabola. This will give f of x1, which is x2. F of x2 will go to the parabola, will give us x3. F of x3 will give us x4, and so on. So that's how, let's say, with a ruler, we can easily calculate the map. And in this case, there's a stable attractor, which is the intersection of the parabola and the straight line. But let's explore what happens when we increase a. So if a is 0, then all initial conditions will take you to 0, no? Because it's just f of x equals 0, and that's it. So that's an extreme case. But if we start increasing a, so for example, here equals to 0.3, well, here there are different initial values. It will converge to 0 eventually. So it's a very small growth rate. So let's say there's some reproduction, but each iteration you will have less and less and less. So it will tend to 0. If we increase slightly here to 0.8, 0 keeps on being a stable attractor, meaning that, let's say, all the initial states tend to 0. And for this value of a equals to 1.1, the attractor is already the intersection between the parabola and the identity line, which is y equals x. This is the identity line. So there's a transition when a equals 1, and in this point, this transition, let's say, for a smaller than 1, lesser than 1, 0 is a stable attractor, and for a greater than 1, 0 becomes an unstable attractor. So it's now like the pendulum upside. And there's a new attractor, which is the intersection of the parabola and the straight line. But precisely when a equals 1, 0 becomes an asymptotic attractor, meaning that it will start converging to 0 the states as you iterate the function, but it will reach 0 only when time tends to infinite. So the limit is 0, but you never reach it. So that's why it's an asymptotic attractor. And also precisely at that point, the intersection of the parabola and the straight line is 0. That's why, sorry, that's the highest value for when the parabola and the intersection is 0. And for greater than 1, then there's a bit of the curve that goes above the identity line, and that's why the attractor becomes the the intersection becomes a stable attractor. But then when A equals 2, we still have this situation where 0 is unstable, and the intersection, which can be analytically derived, it's 1 minus 1 over A, is the new stable attractor. And then when A equals 3, the intersection becomes asymptotic. So we will never reach this state, only when time tends to infinity. And when we increase a bit the A here to 3.1, now the intersection becomes unstable attractor, and there's a new cyclic attractor of period 2. So let's say, assuming we have this initial state, we start iterating, and let's say now it goes away from the intersection, not towards the intersection, but it falls into this attractor, which is of period 2. So it iterates between these two values. So, for example, here, if we are representing a population, it means that the growth rate is such that the population stabilizes, and that's it. It has a growth rate and a death rate that is stable. And here there's an oscillation already. Sorry, where, let's say, in 1 year you have higher population, but then they kind of eat too much, and then the next year it goes down, but then that year they have too much food, so then the next year they go up again, and it starts oscillating like that. And then for A equals to 3.5, the period 2 orbit becomes unstable, and now we have a period 4 attractor. And for A equals to 3.55, now we have an attractor of period 8. So it's not that the previous attractors are gone, it's just that they become unstable. And as we increase the value of A, we start having more and more stable and unstable orbits that pull and push the dynamics. And this is chaos, because you never converge to an attractor. So you are kind of trying to fall into an attractor, but the unstable attractors push you and the stable attractors pull you, and you never reach the attractor in practical time. And this is chaos. So this is what creates the sensitivity to initial conditions. So this can be seen more clearly with bifurcation diagrams. So basically, now on the x-axis, we'll plot the value of A, which goes from 0 to 4. And then on the y-axis, we will put dots where there is stable dynamics. So for A smaller than 1, lesser than 1, the value is 0. And then here at 1, let's say this attractor becomes unstable. And there's a new stable attractor, which is 1 minus 1 over A. And this is called a bifurcation point. Well, here there's also a bifurcation point, but yeah, it's a bifurcation point, and now you have period 2 attractors, and then there's another bifurcation point. You have period 4 attractors and another bifurcation. You have 8, 16, 32, 64, and so on. And then you have chaos. And then you have windows. So for example, here you have a window of period 3. And then if you zoom, you will see other bifurcations, and you will have windows of period 6 and so on. So this is called the Poincaré section, because Poincaré was using this to study the 3-body problem. And yeah, it's like, if we go back, so for example, here we have 8 points, and the Poincaré section will be just if we squeeze all of these to the y-axis and put these 8 dots here, and we go to the value of A and we plot it here, so it's like somewhere here, that would give us those 8 points. And then we will slightly move A, and then we run the attractor, and let's say we start putting the states that attracted dynamics for that value after some time. So if we make a zoom, which part is this? So yeah, well here it's this R is A. So this, you can see more clearly the bifurcations, and you can see clearly more windows. So here there's a window of period 5 as well. And when you reach A equals 4, you have chaos all over the parameter value between 0 and 1. So, I mean, if you, for example, your initial condition is 1 minus 1 over A, you will stay there, but it's like an unstable attractor, and a very small perturbation, it will kick you out, and then you will be all over the state space. Which is why here for 4, let's say it's occupies all values between 0 and 1. And here we can see a window of period 3. So for this value of A, let's say it is the stable attractor. So if you look at this, it's also fractal, meaning that if you zoom on one part, you will see that it's self-similar, so it looks like the original one. And also, it has been shown that you have orbits of period of all the natural numbers. And actually, there's a way of arranging the natural numbers in such a way that will give you this sequence of, let's say, you start with 2, and then 4, 8, and so on, so the powers of 2. And then I forget which one is the next, but the last one is 3. And then that to the power of 2, so it's 3, 6. So it's you have windows of all prime numbers, and then bifurcations for all of those, and that will give you all natural numbers. There's some theorem that will show that that will give you complete natural numbers, and you have orbits of all natural numbers here in this small map. And since it's fractal, if you zoom in that small region, you will have again orbits of all the natural numbers. So it's interesting because it's a way of showing that, I mean, we know that the natural numbers are infinite, but it's not straightforward to show that the natural numbers contain themselves an infinite number of times. And with this, you see, because you have orbits of all natural numbers, of period of all natural numbers. And then when you zoom into a subset of the natural numbers, you will have in that subset again all natural numbers. So yeah, that's an interesting property of numbers and of fractals. So another interesting aspect of bifurcation diagrams is that there's universality in them. So Mitch Feigemann was working at IBM, and even when he had like more powerful computers, he was working with a pocket calculator, say, making measurements of the logistic maps and other maps. And he measured the geometric convergence of the bifurcation points. So I think I have a graph here. So is it this one? Yeah, there are two. No, well, it's a different one. So let me see. Yeah. So if we go to the bifurcation diagram, so if you measure what's the distance between each bifurcation point, so let's say the first one is down here at A equals 1, and then this bifurcation point is for A equals 3. So you measure that distance between bifurcation points, and it will be 2. And then the next one will be the distance between 3 and 3.5 something, which is the next bifurcation point. I measure that distance, and then you measure the next distance, and you measure that distance, and let's say these are these distances. Oh yeah, it's here. So A0 will be the first bifurcation, A1 will be 3, A2 it's this value, and so on. So the bifurcation. So the limit when n tends to infinite of the differences of the let's say one distance between bifurcation points with the next distance between bifurcation points tends to this delta, which is called Feigenbaum's delta, which is an irrational number, but Feigenbaum calculated with high precision. So this 4.66 will tell you, so you could use it to find the next bifurcation point. So if you have, let's say, if you already know this distance, and then you, if you divide this distance by 4.6666, then and you add it to this, it will give you the next bifurcation point without having to build or calculate anything. So that's interesting. This delta is universal in the sense that it describes the bifurcation in all maps with single maximum, because there, I mean, you can change the function of the logistic map. Like there's the 10th map, which is just two straight lines intersected at 0.5, and then you increase the height, and you make the same that we did with the logistic map. And you also get a bifurcation diagram, which looks different, but the distance, the tendency of the, the convergence of the distance between the bifurcation points follows this universal constant. Or you could also do it with a sine function, single maximum, and then you vary a parameter to, with the height. It will also give you a different bifurcation diagram, but also the same universality. And another interesting thing is that this ratio also describes the diameters of successive cycles in the Mandelbrot set, which is a very famous fractal. So let's say you have some structures in the Mandelbrot set, and then as you zoom in, you have some other structures, and then you zoom more, and you have kind of a self-similarity again, and you see the same structures. But the speed at which these structures go smaller and smaller, or well, the radius of some circles in the real axis of the Mandelbrot set. So that's like one very specific structure, but let's say how different scales of the Mandelbrot sets are related can be described with the same constant. Why we have this universality, we have no idea. It's just something that was discovered almost 50 years ago, and I think it's amazing, but it's amazing as pi. No, why pi is the number it is, we don't know. We know how to calculate it. And Feigenbaum found another constant, which is known as alpha, which is this value. And this is the ratio between 0.5 and the closest orbit. These are called superstable orbits. Superstable orbits are those in which the dynamics tend faster to the attractor. And it turns out that for the logistic map, these are found when one of the orbits intersects 0.5. So if 0.5 is in the set of the cyclic attractor, then it's a superstable orbit. So the ratio between 0.5 and its closest orbit, as you increased, that's a different number, but it's also universal section. And the ratio between the distances, so between the value of A here, well, this should be alphas. So, and the value of A here, and the value of A here, and the value of A here, it's also delta. So remember, delta was first calculated with the bifurcation points and how that ratio changes towards chaos. It's called the doubling route to chaos because you have doubling periods of orbits. And so you can do the same to calculate superstable orbits. So if you know this value, then you can use Eigenbaum's delta to calculate the next superstable orbit, and so on. So to conclude, chaos is defined mathematically as sensitivity to initial conditions. Well, mathematically, it's positive Lyapunov exponents, but this means that if you have very similar initial states, this will diverge and will give you very different future states. I mean, not necessarily final states, simply the trajectories diverge exponentially. And with chaotic dynamics, you have an infinite number of attractors that are pushing and pulling the dynamics, and that's what makes it non-predictable. So you can see that this lack of predictability is very different from the lack of predictability of complexity, where you have new information being produced by interactions. Here, the chaotic dynamics are such that your precision is limited. However, in chaos control, there is something called the shadow theorem. So since we have an infinite number of orbits, the shadow theorem exploits that, and it can be shown that for any chaotic trajectory, just like the ones we saw, there is a stable orbit that follows the chaotic trajectory as a shadow. So even when there's an exponential divergence, you can start with such an initial state that will follow that trajectory. So instead of trying to predict what will be the future state, if you want the future state to be something that you, let's say, predicted, then you can, what chaos control tries to do is to push the dynamics in such a way that the system will follow the trajectory that you already calculated, because you know that there's a stable trajectory that follows the one you are calculating like a shadow. So some people would say, well, yeah, chaotic dynamics limits predictability, but just in theory, just in practice, if we had infinite precision, then we would be able to predict the future as much as we want. Well, the problem is that in practice, we don't have unlimited precision, no matter what. So the weather is an example of chaotic dynamics. It's not that we cannot, that we don't know the dynamics of the weather. These have been well described since the 1950s. It means that we don't have enough information to know whether in 2 weeks it will rain or not, because of these trajectories that diverge considerably. And if you start with no information and just predict tomorrow will be the same weather as today, you have like already 50 chances of getting it right. But in order to increase your accuracy, it becomes harder and harder, and you need more and more information. And even when people are putting more and more weather stations to have better measurements, you now have in some applications, they'll have so-called minutecast that will tell you more or less at what time it will start raining. First, it cannot tell you like the day before at what time the next day will start raining. It can tell you, let's say, only for regions that have enough sensors. It will tell you, and also with some limited accuracy, okay, it will start raining in 15 minutes, but not in 17 hours. It doesn't go so far. And in 17 hours, it can tell you, well, it might rain with 80% chance. But it doesn't tell you, for example, which part of the city will have the rain and which part will not have the rain, or which one will be flooded and which one won't, like in places where you have such distinct rain patterns. So, I mean, people are working on this because there are many applications for this, but inherently there are limits to what we can do with chaotic dynamics, and of course there are different attempts to not so much overcome them, but let's say to understand them better and try to extract as much information as possible. So Roberto asks whether there are any Bayesian-based approaches to chaos dynamics. I think there have been several works that use, for example, neural networks to try to predict chaotic dynamics. I don't remember how successful they've been. I remember they did it, but not what was the result. I mean, I suppose they were able to predict some of it, but it's not that, okay, now with neural networks, chaos is predictable. It wasn't like that. Yeah, another thing, if you just have the data and it looks chaotic, it becomes very difficult to extract, say, the equations that generated that data, because it's like it could be so many things, and since the trajectories are chaotic, it's not like, oh, it should follow this trajectory and then you just kind of make an approximation and kind of fit your data to a function, because let's say if the data is all over the place, there will be no function that will fit properly, or there are so many functions that will fit that data with a certain range that you cannot trust that you got the right one, because there are so many that will kind of give you similar degree of precision. So for the next classes, we'll start seeing concepts and history of cybernetics, which already set the basis for the study of chaos and complexity and adaptivity. And for next week, the homework will be to have a short comment, less than 500 words, of the article Behavior, Purpose, and Teleology by Rosenbluth, Wiener, and Bigelow. And we will discuss it next Thursday. So yeah, but by Thursday you should have read it and commented it, and then we'll discuss it on class. So it won't be so much a lecture as a seminar. So yeah. I will put on the Google Classroom the paper so that you can get it. I mean, very probably you will get it on your emails, the announcement, or not. No, I think you don't get the new announcement. Well, it will be on Google Classroom, so you can check it in an hour or so. Are there any questions?
No one, I think.
Well, it's good that we have some time left, because I wanted to ask you to share examples of complex systems, but not your examples, but some example that you read of one of your classmates that you liked, and tell us the example and tell us why you liked it. So you can just raise your hands or write on the chat. Yes, Elliot.
Yeah, I think that was very interesting, the example of the social movements. In fact, I think that revolutions are something like a critical state, no, where population is very sensitive. Then I get interested in that aspect. Thank you.
Yeah, it's interesting in societies that you can have also similar phenomena as the one we saw with chaotic dynamics. So another aspect that we will see in future classes is robustness, how systems are robust, how can we build robust systems. But in social systems, it's also relevant how to break down robust systems. So for example, dictatorships tend to be robust in the sense that they remove opposition, so it's difficult to change. And revolutions are usually the only way of changing a very robust system, social system. So it's like, okay, you cannot change it slightly, you have to break everything and start from scratch. Or yeah, we'll see more concepts that will be also useful to understand social systems. And of course, your predictability there is limited on different fronts and at different scales. So Fernando asks on the chat, a close to zero Lyapunov exponents can characterize any kind of critical behavior. I'm not sure whether it's easy to derive the Lyapunov exponents of any dynamical system, but if you can do it, then yes. It could be used to define criticality, but I don't know how easy would it be for any system, especially if, let's say, you have data but not formal. Let's say you don't have equations that you have derived to model that data. Yeah, I mean, I'm sure there are some techniques to derive the Lyapunov exponents, but yeah, I don't know whether it can be generalized to all critical phenomena. But if you can calculate the Lyapunov exponent and it's close to zero, then you could say that it's critical. So you asked whether Lyapunov exponent is related with the first exponent. Let me check what's the first exponent. If anyone knows, please. Long-term memory of time series. It relates to the autocorrelation. So it relates to the autocorrelations of time series. Yeah, I wouldn't be able to answer straight away because very probably there is some relationship, but which one is it? I don't know. Yeah. Any other questions or examples that you like?
I wanted to talk about the example that I think it was Harodi. I don't know if he's here, but he was talking about how science is affected by a lot of factors, including like political pressures or pressures from the private industry. And I felt a little bit, I don't know if I could say offended, but a bit alluded because I believe myself to be a part of the scientific community. And I do understand that, well, it is very clear to me that scientists are human and that humans sometimes lie or make mistakes and stuff like that. And they do get affected by the economy and by other factors. But it just is a little bit troubling during these times in which, you know, the president has criticized the scientific community. And I do want to bring it up because I've talked to a lot of people who think that science is this perfect system, you know, with its perfect methods, and it's very rigid, and it's very, whatever you say as a scientist must be true. And I think that's a big mistake. And I wish to change that point of view and see what you guys think about it. Thank you.
Yeah, I think that you can go to several extremes that are mistaken. One, as you mentioned, is to assume that if science says so, it has to be true, because precisely what makes science scientific is that you doubt of everything. So that's how you avoid dogma. And the other extreme would be to say that every science has an ideological agenda. And I think that science cannot be purely objective, in the sense that, of course, we are motivated by our context and what our interests and our desires and our passions. I mean, we're human, but I don't know. Yeah, I mean, I don't think that we should go to the extreme of, I don't know, this expression of neoliberal science. I try to understand in which context it's framed, but I think it can be misguiding. But Rodi is here, maybe she would like to answer.
Yes, sorry to upset you, Sophia.
No. On the contrary, I was thinking, actually, I had thought about it in the past sometimes, and you brought it up, and I think it's fascinating because it shows how complex science is.
Yeah, I was maybe referring only to the publishing system, because I don't know, I'm trying to share my code and try to I don't know, like talk about topics that are not that popular, so they can be uplifted. But I think that the people that are doing science, yeah, it's are driven by this kind of political interests and economic interests, just like me, because I want to make I don't know, I'm from the social science. I want to make a difference, a positive difference, and maybe that's why I'm focusing on this topic. I think, yeah, I don't know what else to say, but it was more on the publishing system that I was criticizing.
Okay. I do agree with you. I agree, actually. I just don't want to agree, you know?
Yeah.
It's hard to accept the one's mistakes and faults.
Yeah.
Last year, Danny Bassett gave a seminar at the C3. I posted the link in the chat. I think it was in the seminar where she contrasts different theories, well, with some colleagues of scientific discovery. So it's basically, well, if you took a course on philosophy of science, probably you remember that there's like Kuhn's theory of scientific revolution, and then there's Lakatos' theory, and I don't remember if also Feyerabend she considered. But let's say there were these theories, and they kind of mined the data from Wikipedia, and they were able to show evidence for Kuhn's theory. And then you can also see this reflected on publishing patterns or in funding patterns. And actually, this is also related to the science of success, because Dashun Wang gave also recently a seminar in the same series. So you will find in the same playlist, you will find the talk by Dashun Wang on the science of success. And he speaks about the research of success in scientists, in film directors, and painters, I think. Well, it's three professions. And they found that there are some patterns that they have a hit and then a lull, but these so-called hits, or let's say, you can say that scientific advances are not just by innovation, but there's innovation and then or exploration, and then you have exploitation. So first there's something new, and then there's developments on that new thing. If you are just new, then you're not taking advantage of the new things. And most established sciences make it or push it towards extending what's already there than to exploring new things. So papers that are innovating are more difficult to get accepted. Projects that are innovating are more difficult to get accepted because usually people judge with what they know, and if it's innovating, then you don't know. So it gets difficult to within science to be innovative. And it's also interesting, a recent study about high impact papers, it turns out that the innovation papers are more multidisciplinary and they are made by smaller groups than the extending papers that kind of take some innovation and kind of put it in a stronger foot. Those are more disciplinary groups and they're larger on average. So it's interesting that we are able to learn about this only in recent years. And I'm sure that there will be interesting things in years to come.
Sorry, that has to do with something that Sophia said also in her homework, because this system is so complex that you cannot expect to make a difference in the way science is being is doing. But just because you are working with different scientists, you can innovate it easily.
Yeah, and also Odin wrote about Roberta Sinatra and Laszlo Barabashi and their group at Northeastern University. So I mean, they have several papers, but one of the main ones, so they were interested in trying to predict whether scientists were good or not early in their career. So what is the probability of, let's say, having a high impact paper that might lead to a Nobel Prize or something like that in your career? And analyzing the data of several Nobel Prizes, they found that, well, also there was this idea that if you don't make a breakthrough, especially in mathematics, by the time you're 30, then you will never get one. And Roberta and her co-authors managed to show that this is just a myth. You have the same probability of producing high quality papers, or let's say breakthrough papers throughout your career. It's not about your age. It's just that usually, on average, when you are younger, you publish more than when you're older. So it's like the same probability, but then you're basically buying more tickets for the lottery when you're younger. So she says, like, to other researchers, so don't give up hope that you will be able to make an impact. Just that yeah, you cannot predict whether a scientist will have a breakthrough or not in the future. Because let's say one of the things that funding committees or hiring committees would like to know is like, okay, we know, I don't know, 7 years or 10 years of career of young scientists. Should we invest in them or not? And of course, you would like to predict that, and what they show is that you can't. So you have to take a gamble. There are, of course, there are things that you can tell, but they're not different from what you would know already. So let's say if by 10 years they haven't published much, then let's say chances are very low. And if they already have publications and these have had lots of citations, then of course they have much higher chances. So, yeah, they kind of try to calculate a parameter that's independent of time to measure the impact of scientists. Yeah. Okay, so let me search the chat because Domingo Islas wrote, I like the brain example because I consider it to be the most important topic in the study of complex systems, since it will allow us to learn how to replicate dynamic and produce artificial brains to help us. This is a good comment because it shows like some of the expectations that complexity has shown to be misguided, in the sense that when the Human Genome Project began, they promised, oh, once we have the full human genome, we will have broken the code of life. And this will give us access to cure all the genetic diseases, and we will be able to do this and that, and it will be for the benefit of our humanity. And well, many things promised. Give us the money, and that's how they funded the project for several years. And once they finish, it's like, okay, when are the cures for cancer coming? And I mean, we're still waiting. And it's like, well, yeah, but it turns out that the proteins are also relevant. So let's start the human proteome project. And then after some years, well, yeah, we need also to study the interactome. And I mean, it's never ending, because the Human Genome Project gave you the bricks, but it didn't give you the interactions. And those are not only more difficult to obtain because it's not sequencing only, they're dynamic because the way genes or proteins interact with each other can vary depending on other genes. So it seems that it's a non-tractable problem. I mean, it doesn't mean that we shouldn't fund that research. It means that it will not give us the key of life. And it's similar to the brain. A few years ago, there was how much money was it? I think, I don't remember if 1 billion euros for 10 years for a project on the brain, pushed forward by Henry Makram from Switzerland. And after 1 year, they started evaluating, and they thought, how did they approve this project? All that they promised is not achievable. they promised like the heaven and earth, and they gave them the money. And I don't know whether that project is still going on, because it was clear that they wouldn't deliver. So I don't know whether they stopped it and cut the funding, or I don't know what happened. It was kind of embarrassment for the European Commission for having funded that and not other projects where we were participating, of course. But yeah, in the introduction of one of his books. I think it's I forget the title of the book, but it's something about the brain of Michael Arbib, and I think the book is from the late 80s. And he says something like, if we had a full model of the brain, like, okay, neuron by neuron or molecule by molecule model of the brain in a computer, that wouldn't be more illuminating than the brain itself. So we need simpler models of the brain that will allow us to describe brain dynamics, but at a higher level of detail. So, yeah, I mean, understanding brain dynamics can give us insights into developing some new algorithms. But let's say in machine learning, even when they still use the name artificial neural networks, they have not that much to do anymore with how the brain works. I mean, there are some mathematical analogies, but as engineers, we're more interested in things working. So basically, you fiddle with the model until it does what you want decently well, and that's it. That doesn't give us a greater understanding on what mind is, what consciousness is. So I mean, the limitations of studying cognition are still there. And also, yeah, there are different studies of brain dynamics, and some say that it's chaotic, and some say that it's critical. Yeah, I guess it depends on precisely what you're measuring, but what we have done is to understand, like, okay, what's the benefit of having critical brain dynamics, but not so much as to being able to predict, let's say, like from a brain scan, trying to predict what you're thinking or what you will decide. That's I wouldn't say far away. I would say not possible with tools we have now. Giving our understanding of complex systems, it's not so much to being able to do more things so as to understand different phenomena and be able to describe more precisely the limits of the things we can do. Okay, so let me go back to the chat. Odin writes about this example. It turns out that much genomics assumes non-complex genotype to phenotype mapping, and that's a source of lack of success. But not molecular biologists. Yeah, yes, they are a good example of reductionists. That, okay, there's this gene, and this will make you gay if it's on, and it will make you straight if it's off. And it's like, that's not how genes or sexual preferences work. But anyway. Already writes, also, even if we get to model interactions within the brain, we will be still missing interactions with the body and the environment. And yeah, that's criticism from inactive embedded cognition. Eli writes, in hurricanes are confident of weather models, but these are incomplete. Well, they're incomplete because, of course, you don't have full data of the different scales at which you have dynamics. So in chaotic systems, you have self-similarity, meaning that there's no characteristic scale. And this gives you also power law distributions and some other fancy things that have been studied within complex systems. So what this means is that if you have a characteristic scale, meaning that I don't know what would be something, the characteristic scale. let's say, height in humans. You can say there's an average height of, I don't know, 165 or something like that worldwide. And then with a standard deviation of 30 centimeters or whatever in adults. And of course, you have outliers. I mean, people measuring more than 2 meters 10, people measuring less than 140, and but let's say there's a characteristic scale. I mean, there are no people measuring 10 meters or 100 meters or 1 kilometer. And this allows you to design, for example, chairs or airplanes or cars or houses that, let's say, with given certain margins, they would be good enough for everyone or the majority of the population because of a characteristic scale. Now, there are phenomena without a characteristic scale. Perhaps one of the common ones is earthquakes, in the sense that, of course, you can calculate what's the average earthquake in, let's say, that is measured in Mexico City, but that doesn't give you information. You want to be able, I mean, there's this, actually, there's a recent book by Didier Sornet and another person. In China in the 1970s, they had a whole program to try to predict earthquakes. And the problem is that they had a success. So they had some measurements and they told, hey, there's a big earthquake coming. And it came. So it's like, hey, yeah, we were able to predict earthquakes. But then a few years later, they couldn't predict another one. And I don't know, I haven't read the book, but see, they tell this story and what's the limits of earthquake prediction and prediction of similar phenomena like market crashes and weather and so on. But yeah, you want to predict the outliers. And also, there is no characteristic scale. And they have scale-free distribution because you have lots of small earthquakes that are almost not felt, and you have very few big earthquakes, which are the ones you care about. Yeah, but by having no characteristic scale, that also limits prediction, and that's also sometimes a consequence of chaotic dynamics. So it's in similar direction. So Odin writes, a lot of your comment is super relevant to people in robotics. They call it embodiment. It seems when they play the simulations in real robots, all crash down. That's not entirely true. So yeah, I mean, this criticism is like from the 80s and 90s. I mean, actually, part of artificial life was created in using this criticism, and in parallel, well, in Europe and in the United States, there was so-called behavior-based systems. There have been, I think they're still ongoing, it kind of faded out. There were some conferences on the simulation of adaptive behavior, and there were still is, I think, International Society of Adaptive Behavior, which were criticizing this approach of, they would call it good old-fashioned AI, GoFi for short, trying to predict the movements of robots and things like that. And so already in the 90s, some people realized that if you are going to, for example, evolve some controllers for robots in software, and then you will download into a robot, if you add noise to your simulation, that will make it much more robust when you transfer it to real robots. Because if in your simulation you don't include noise, then you assume that the sensors are perfect, that the motors are perfectly aligned, that there's no difference. So you might get one solution that works very nicely in the simulation. Then in the real world, you have the noise and they don't work. But if you add noise, then they do much better. Josh Bongard has been making several experiments in evolutionary robotics in recent years, and they do the same, and they do transfer successfully their genetically evolved models to to robots and more recently to xenobots. Perhaps you saw the news. They're robots made of embryonic frog cells. So they evolved in the computer the shape of robots that's made of cells. So it's not a metal, but a living robot. And it's like, okay, how can we organize cardiac cells and skin cells to have movement? And then an evolutionary algorithm, after several generations, told, try this shape. And then a very able postdoc managed to manually separate the cells of frog embryo. That's, I understand they work with them because they're relatively big. So each cell is very big, so you can actually manipulate it by hand, even when they're, I mean, you need to watch it with microscope. And he built these robots and they move. And then they went a stage further, and these robots were also able to swim. And then they noticed that these swimming robots were able to kind of gather cells that were just floating around in their petri dish. So they kind of move and push other cells, and then these cells become aggregated, and they gave them a shape like a Pac-Man shape. So they have like this mouth. So so they're able to push better around the cells, and when the cluster of cells that they built reaches a certain size, then they become another xenobot. So it's yeah, you could call it reproduction, which is very limited because, of course, these things don't eat. So when the cells die, they die. They last a week or less, and then these reproducing xenobots, each generation, they become smaller and smaller. And once they are too small, they cannot gather cells successfully.
It was incredible because in the last Artificial Life conference, it was a lot of people working now with those volumetric 3D robots based on squares. And many of them were saying, like, now we need to make them real robots because they are super useful.
Yeah. Yeah. Okay, so back in the chat, Elio writes whether interactions are independent variables. Not necessarily. Yeah. Okay. I saw that we're already over time. So if you haven't commented on the examples of your classmates, please do it today. And we'll see each other on Tuesday to speak about cybernetics. And later today, I will post the next homework for next Thursday. So have a great weekend and stay safe.
Thank you.
Thank you all. Bye. See you on Tuesday.
Elliot, if you want, you can post on the classroom whether anyone wants to organize to play with NetLogo for weather, and if the interested people can already organize.